My previous lectures on Quine and Davidson were the last ones about the history of analytic philosophy. I want to give you 3 special lectures on specific topics dealing with philosophy and language. And today I want to explain the connection between study of language and artificial intelligence. My lecture will have 3 parts. In the first one, I'm going to talk mainly about Alan Turing, who thought that digital computers can think. In the second part, I will criticize Turing's position, mainly on the basis of works by John Searle, who thought that Turing was wrong and that there cannot be anything like thinking digital computers. And in the third part, I'm going to criticize Searle on the basis of William Rappaport, who thought that Turing was right from the beginning and that there is a possibility of thinking digital computers. But the main hero of this lecture is Alan Turing, a handsome fella who was born in 1912 and died in 1954. Turing was a British mathematician, logician, computer scientist and also cryptanalyst. During the World War II, Turing worked for the army in Bletchley Park and he was code-breaking Enigma machine. I hope you've heard about Enigma. Just for starters, it was an encrypting machine that was used by Germans for encoding and decoding secret messages. And Turing was one of those guys who code-breaked the machine. After the war, Turing co-created one of the earliest store program computers, Manchester Mark I. And this is the reason why Turing is quite often called the father of computer science or the father of artificial intelligence. Unfortunately for Turing, in 1952, he started to be investigated for homosexuality. In the 50s, homosexuality was still a crime in the United Kingdom, and after the trial, Turing had to choose between imprisonment and probation. He chose probation. That was based on hormonal treatment designed to reduce libido, and it was based on injections of estrogen. I must say that I do not understand why homosexuality would be treated by estrogen. It doesn't make any sense to me. And Turing suffered a lot because his hair fell off, his breasts grew, and he was very depressed about the situation, and that was maybe the reason why he, according to some historians, committed suicide. He died of poisoning by cyanide in an apple. There are other versions of his death. For example, his mother thought that it was just an accident, that Turing was not very good in hygiene, and because he did some experiments in his bedroom and he used cyanide in these experiments, it might have been an accident. I'm not sure if we could know what was the reason of his death, if it was an accident or a suicide. In any way, his death was, of course, tragic. Turing's life was very interesting, and this is the reason why there are a few movies based on the events of Turing's life. Probably the most famous one is The Imitation Game from 2014, starring, as you can see, Benedict Cumberbatch. Well, everyone loves that film, but I hate it because it's very untrue to the reality of Turing's life, and I do not think that you need to improve anything in there because it's spectacular. I mean, the life itself, you don't have to change anything. It's so interesting. And the film, of course, changed a lot. But I want to talk about works by Alan Turing. During his lifetime, he published just 2 quite short papers, but they are heavily influential, both of them. In the first one, that was called On Computable Numbers, with an application to the Entscheidungsproblem, he described digital computers. He was the first one who tried it. This paper was published in a mathematical journal in 1936, and this text is the reason why till today we call digital computers Turing machines. Terms digital computer and Turing machine are synonymous. But for us, probably more important will be the other text that was published in philosophical journal called Mind, one of the most prestigious philosophical journals in the world, in 1950. It is called Computing Machinery and Intelligence, and Turing tried to answer the question whether digital computers can think. Turing wasn't the first philosopher who asked whether machines can think. For example, René Descartes asked exactly the same question in the 17th century and answered with categorical no. Machines cannot think, only humans can. I believe that Turing was the first one who answered this question in a serious manner. He thought that the question itself is too vague to be answered. There are two problematic terms, machines and the verb to think. Turing thought that the term machine can be defined in a simple way. It's just a digital computer, he described in his previous paper from 1936. But the problematic part still is what to think means. According to Turing, we have to reformulate the question to this. Can there be digital computers that could do well in the imitation game? And imitation game stands for the verb to think. It is a party game, let's say. It has, in a very simple version, just 2 actors. The one is a referee, and the second one is a person or a computer that tries to answer referee's questions. And on the basis of the answers, the referee has to decide if he talks to a person, a human being, or to a digital computer, a machine. There are some sample questions from Turing's paper from 1950. For example, a referee can ask, please write me a sonnet on the subject on the 4th bridge. And the subject, whether it is a human or a machine, answers, count me out on this one. I never could write poetry. You can see that the questions and answers are quite sophisticated and they are quite persuasive. Another question might be, add 34,957 to 70,764, and after few seconds of thinking, the subject answers 105,621. The pause for thinking is important because humans, of course, cannot count as fast as computers. Next question might be, do you play chess? The answer is yes. So another and the last question in this example is, I have king at my k1 and no other pieces. If you have only king at k6 and rook at r1, it is your move. What do you play? And again, after few seconds of deciding or thinking, the answer might be r to r8 mate. We can see that these questions are not simple. They need a lot of knowledge and a lot of linguistic abilities to create satisfying answers. You have to think, according to Turing, to be able to answer them. You can see that Turing was also a linguistic behaviorist, and a behaviorist in a more general meaning, in a more general sense. So the thing is that Turing was in the same school of thought as Wittgenstein or Quine or many others. Turing was very optimistic about the possibility of thinking machines. He believed that in the near future we are going to have computers that will be able to pass the imitation game, or so-called Turing test. In the end of his 1950 paper, Turing wrote, "I believe that in about 50 years' time, it will be possible to program computers with a storage capacity of about 10 to the 9th power to make them play the imitation game so well that an average interrogator will not have more than a 70% chance of making the right identification after 5 minutes of questioning." The original question, "Can machines think?" I believe to be too meaningless to deserve a discussion. Nevertheless, I believe that at the end of the century, the use of words and general educated opinion will have altered so much that one will be able to speak of machines thinking without expecting to be contradicted. This means that according to Turing, in the year 2000, we had, allegedly, computers that were able to pass the Turing test. Well, we didn't get them. Or did we? Today, we might not have thinking digital computers Alan Turing dreamt about in the 50s, but we have chatbots. These are quite simple programs that are based on so-called pattern matching, and the most famous chatbot was probably Elisa from the 60s. It was very simple, as you can see on the screenshot on the right side of this slide. Elisa tried to imitate the behavior of Rogerian psychotherapist, which means that the reactions of the chatbot were very simple and quite vague. Pattern matching means that the program is able to recognize some patterns in the input in the questions, and it can create vague answers based on this pattern. For example, if you mention in your talk the word mother, computer can produce an answer about mothers or other family members or something like that. Since 1993, there has been an attempt to recreate Turing test in the real world. It's called Leibniz Prize and it has been organized by University of Surrey. In comparison to Turing's original version of unrestricted test, where you can talk about anything for quite a long time and everything was allowed, this Leibniz Prize is restricted. The test is restricted. It can last only 5 minutes. The topics are selected up front and there cannot be no tricky questions, for example about self-reference or stuff like that. And you also have to use the language of a 12-year-old. The interesting thing is that people are quite gullible and they are charitable when describing the computers in this test. They usually fall for them. This effect is sometimes called Barnum effect in psychology, and there's a nice illustration of that. Barnum effect means that people find something in anything. They believe that everything is important, and when you give them some vague input, they usually believe it just because it's about them. This is the effect why astrology or card reading works. In 2014, in another restricted test, a short program called Eugene Gustman won at University of Reading. This Eugene Gustman was a very simple program that tried to imitate the behavior of non-native speaker, a small Ukrainian boy, and allegedly the language skills of this Eugene were not very good. The results were quite surprising because referees really thought that they were talking to a real boy. I know that the rules were somehow, I don't know, corrupt in this case, because it's not what Turing had on his mind in 1950 when he described the test. And there were some attempts to trick these tests, like for example by a program from the 70s called Perry. Perry stands for paranoid. This tried to simulate a thinking of a paranoid person, which means that during the test the answers didn't have anything to do with the questions and they were a bit paranoid. If you ask, for example, this chatbot what the weather is, it asked, or it answered, "Why do you want to know? Who are you? Are you following me? What do you want to do with me?" or something like that. Typical reaction of a paranoid person. I wouldn't take these examples too seriously. For example, a very famous programmer Joseph Weizenbaum, the creator of original chatbot Eliza, had this idea in 1973 that he could program very simple chatbot called catatonic that would simulate a behavior of a catatonic person. It would not answer at all, and Weizenbaum said that this program would have an advantage, that it wouldn't need a computer at all. A terminal or keyboard that would be connected to nothing would suffice, would be enough. Forget chatbots. Let's talk about more serious criticism of Turing test. The most famous reaction came from John Searle, an American philosopher of language and mind. I discussed Searle before in my lecture on Oxfordian School of Ordinary Language Philosophy. Searle was a co-author of speech acts theory together with John L. Austin. Searle studied under supervision of Austin at Oxford University, and now he teaches at the University of California in Berkeley. In the 1980s, he created a very famous argument against strong artificial intelligence. This is an artificial intelligence that was promoted by Turing and Weizenbaum and others. He wrote a very influential paper about the topic in 1980. It was published in a very prestigious journal called Behavioral and Brain Sciences, and the paper was called Minds, Brains and Programs. This is going to be a required reading for this week. In his 1980 paper, Searle devised a very famous thought experiment, usually called Chinese room argument. You have to imagine a person that is entrapped in a room with just two windows. In the original formulation of the argument, the person was Searle himself. Searle cannot speak any Chinese. He is in this room with a very large manual of all possible reactions to Chinese symbols. The point is that if someone throws a piece of paper with the Chinese symbols on it, Searle cannot read and understand the symbols, but he can find an answer to them in the manual. And he can find an answer and throw it out through the other window. According to Searle, it means that person outside could think that the Chinese room understands Chinese and that it speaks Chinese. The point is that it doesn't really, according to Searle, because the person inside doesn't understand any Chinese. And of course, this is just a metaphor for how computers work. They can match inputs to outputs based on some hardwired program. This is the book of instructions, the manual of instructions. And it can look that from outside the computers understands the symbols. But the point is, according to Searle, again, that it doesn't. In his later writings, Searle provided a formal proof of his argument that computers cannot use language and therefore they cannot think. The version I'm going to show you comes from a companion to the philosophy of mind that was published in 1997. It comes from the entry John Searle that was written by John Searle himself. That's nice. According to Searle, his argument has three premises and a conclusion. First premise is programs are formal, syntactical. Second premise, minds have contents, semantics. The third premise is syntax is not sufficient for semantics, and the conclusion, according to Searle, is programs are not minds. Computers cannot think. I don't want to criticize this argument right now. I'm going to get back to it after a few slides. But I just want to point out that there is a problem, according to me, in the third so-called premise. I think that this is not a premise at all, because how can we know that syntax is not sufficient for semantics? It is just something that Searle says without any evidence. We might have this intuitive feeling that syntax is not sufficient for semantics, but I would like a proof that this is a sound argument and that this premise is really true. The required reading for this week is, unsurprisingly, Searle's Minds, Brains and Programs. And I have 4 questions for you to answer. The first one is, what does Gedankenexperiment in German mean? Second, who is in the Chinese room? Third one, how does the person deal with Chinese symbols? And the fourth one, what is the conclusion of the example? I know that I gave you some hints in my lecture, but I would like you to find the correct answers in the text itself. John Turing is very confident that he is right when criticizing Turing test and strong artificial intelligence. In the year 2008, he gave an interview to a philosopher, Julian Baggini, and he said this: I hope we have recovered from the behaviorist phase in the philosophy of mind. I think we have overcome it, and I think we have pretty much overcome a similar mistake, the computationalist phase. Just as it is wrong to think the mind is nothing but behavior and dispositions to behavior, so it is wrong to think the mind is nothing but a computer program or a set of computer programs. These were disastrously wrong turns, but as I said, I think we are overcoming them. You can see that Searle's theory is very close to Chomsky's stance. Both think that behaviorism, mainly linguistic behaviorism, is wrong. And they do not believe also in computational approach to the mind and language. Unfortunately, I don't think that Searle's criticism is sound. I have at least 3 objections to his Chinese room argument. Let's have a look. The first objection might be this one. Chinese room argument is just a thought experiment. I'm not sure if we can come to conclusions based only on our ability to imagine something. We can imagine almost anything, but are these results really true? I think that we usually base these results, these conclusions, just on our intuitions. And I would like a proof that our intuitions are true. The second objection is usually called system objection. According to this one, we really cannot say that Searle entrapped in the Chinese room understands Chinese. We also cannot say that the processor of a computer thinks and understands. But we might be able to say that the whole system of the Chinese room understands Chinese in the same vein as the whole system of the computer thinks and uses language. The processor itself is probably not enough, but the whole system, when we take it together, might be a thinking object. The last objection is usually called syntactic semantics. I'm going to talk about it for a while in my next slide. When talking about syntactic semantics, I have to start with this girl, Helen Keller. She was an American writer, a lecturer, and activist. That is quite surprising because when she was 19 months old, she contracted an unknown illness that left her both deaf and blind. Fortunately for Helen, with help of her instructor Anne Sullivan, she learned to communicate in tactile signing. This is a special kind of alphabet that is based on tactile stimuli. It usually means that you touch each other's hands and you sign using these touches. Helen Keller wrote a book on her language acquisition, and she describes some important milestones in this process. For example, the first object she could have referred to was a doll. She just touched a doll, and then Anne Sullivan signed in a tactile way the word for a doll, and Helen somehow connected these two kinds of stimuli together and understood the difference between objects and the symbols. Then she could have moved to more abstract terms like water. When she signed water for the first time, she thought that it is just a sign for a water in a glass. Later on, she started to understand that it's also a river in a brook or a lake, or water that is falling down from the sky when it is raining. Helen was the first deaf-blind person to earn a Bachelor of Arts degree, and she is the main hero of academic paper by William Rappaport that is called How Helen Keller Used Syntactic Semantics to Escape from a Chinese Room. This was published in a specialized journal on artificial intelligence called Minds and Machines in 2006. To understand Rappaport's argument, we should define what syntax and semantics is. We can use a classical textbook by American linguist Charles Morris. In 1938, he published Foundations of the Theory of Science, and in there he defined syntax and semantics in this way. Syntax is the study of relations among the members of a single set. This single set is a language, and the members are words. Semantics, according to Morris, is the study of relations between two sets. On the left side, you can see the language, words included, and on the right side is the world, and the members of this set are objects. According to William Rappaport's argument, the difference between words and objects, the difference between language and the world, was not very clear in Helen Keller's case. Objects and symbols were members of the same set, the set that was based on tactile stimuli, on touching. Rappaport wrote, Syntactic semantics claims that first-person understanding is just this sort of syntactic manipulation, and the more ways there are to manipulate the terms, the more understanding there will be. Which means that Helen Keller's semantic understanding came via linking of internal representations of two external experiences, touching and signing. But this signing was based on touching too, which means that there was just one kind of external experience based on, again, tactile stimuli. You should understand that the set of things Helen Keller had access to was just one, and its members were symbols and objects. The way to both objects and symbols was based on tactile signing and tactile touching. I should probably end my lecture here, and you should understand that William Rappaport's argument was for the possibility of computers escaping Chinese room via Helen Keller's example. I hope you understand that this lecture was quite complicated, but that it had three parts. In the first part, I tried to explain why Turing thought that computers can think. In the second part, I showed Searle's criticism of Turing test and strong artificial intelligence. And in this last third part, I again tried to defend Turing's theory of thinking computers based on Rappaport's syntactic semantics. I agree that these questions are very complicated, but we can continue discussing them at our online meeting.